making the short drive from Greencastle down to the pecan plantation, or pecan plantation, depending on which way you pronounce that. I grew up in Missouri/Missouri/Missouri, so debates. He wondered if I'd talk a little bit about the physics behind energetic particles and seeking energetic particles. So that's what I want to. This is not much of a radio talk. It's not much of a high-altitude balloon talk. We'll get a little of that as we get to the end of it. Don't work that way. And it also made me reflect on the fact that I got started in this, don't be offended, but this game about 10 years ago next month. I went to the Accessing Technology Across Indiana conference, which has nothing to do with balloons. But at the end of the program, it was at Taylor in Upland. At the end of the program, they announced that there was going to be a high-altitude balloon launch at the close of the conference. And so I thought that'd be fun to watch. Turned out it was a young man who had been and lived in the same door as our older son who graduated the year before. He had this little startup company using what winds up being a 900 megahertz spread spectrum stuff that we do and deal with. And also he did a high-altitude balloon launch, and I watched it go up. And there was also a rather energetic particle there, a man who was quite interested in it and quite knowledgeable, and he was quite willing to explain to me that the balloon was going to go up. It was summer, it was July, it was going to track east for a while, it was going to turn around and go west for a while, and then it was going to burst, it was going to go east, and it was going to land about 6-8 miles northeast of the launch site. And he went on and has gone on with the balloon flight for about 2 hours, and he kept answering questions for me, and he kept telling me more and more things about the high-altitude ballooning. And I thought, well, that's kind of interesting. And so I went home. Actually, I called home in Maryland first to tell her I was going to be a few hours late because Upland and Greencastle were just a short 2-hour drive apart. By the time I got home, the balloon was still coming down. And then I had to wait to hear that it was indeed in good old Indiana corn, which is not Nebraska irrigated corn. Okay? Indiana corn is only about 6 foot tall, but make sure the payload came down. And so I went home excited about it, thinking I might want to do something with it. And of course, I thought, this energetic man, he shared my name. He's sort of an interesting thing. So the first energetic particle that I saw, next slide, is a very famous energetic particle that we all know. That's how I met Bill Brown. And he introduced himself to me as Bill Brown because I was not a ham at that point. Took a little digging to find out that there was this sort of collection of alphanumeric characters. Now I'm KC9QBN and in the game after a few years of deciding that 900 megahertz wasn't the only way to go. So next slide, sweetie. Don't panic, it is blank. Time for a disclaimer. My day job is a professor of physics. Okay? What you're going to hear today, we normally have one course where we spend 7 weeks in it, which is a course that we follow after an introductory course where we spend about a week and a half in it. Okay? And John is sitting over there with his watch to make sure that I don't spend more than an hour in it, and I know most importantly that immediately after I get through, it's lunch. Okay? So I want this to be interactive. I'm going to force it to be interactive. Actually, I'm going to be so interactive you go out to get a profit a minute, which I'll get a little later in the talk. But I'm going to ask you to respond every once in a while because depending on when you went to college, it might have been the professor gets up in front and he starts or she starts, and the end of the class period comes and they stop, and you come back the next day. And the best one I ever had was he stopped in mid-sentence and he picked up with the next word the next day. And I noticed he always had this little stack of yellow paper, and it turned out it wasn't that legal pad that comes yellow. It had started white. I don't want that. We're going to have interaction with people that go through, and we're going to deal with this stuff. And so just that's my caution. Okay. So, first important things, we have some fundamental principles that are involved. The first one of which is nature does what nature does. Next. Things happen. And finally, the third important point is that science just simply models. The scientific models are just an effort to try to explain what we see. The models are not reality. I really appreciate the work that Mark was sharing and all that he's doing with that. High-speed data collection, I consider 50 hertz high speed, allows you to see lots of fascinating things that you miss when you chirp every 30 or 60 seconds. So it's great to get that stuff. But these are all just models we're dealing with today. So we're going to talk about fundamental particles. What do we mean? Next. What are the basic building blocks of what we're dealing with? And we're going to look at this from the beginning. So let's go back to the ancients. That maybe some of us in the room. The ancients thought that there were 4 elements that made things up. Do you remember what the 4 elements that the ancients, I'm probably talking about early Greeks, Egyptians.
Fire, water, air, water, and earth.
Earth. There you go. Okay, next. You did good. You did them in the right, almost got in the right order, but that's all right. Okay, it works out. So air, fire, water, and earth. And everything was made up of it. It was 4, and it's a nice, simple sort of thing. That ought to be fundamental. I mean, 4 fits on a hand. That's kind of convenient, so it works out there. So that's where we started. However, going a little longer, the later Greeks got to the idea that there were a greater variety of things. Okay, and they identified this thing they called an atom. Okay, who knows their Greek? Why is it atom?
Indivisible.
Indivisible, yeah. No cut, right? Tome comes from tomas to mean to cut, and the means you can't cut, right? So they came up with the idea of the atom, and so we're going to skip a few centuries, because I went every century forever. We would come up to the 1800s, and by the 1800s, Mendeleev's put together a periodic table, recognizing there's quite a number of different types of atoms, right? The good old standard periodic table would have stopped at 92. Since that time we found a way to make 93 and 94 and 95 and 96 up to what, 116 or 117 or something? 118? 118, okay. I'm not a chemist. I don't play one on TV. Those elements are out there in a way. So that led us to the last part of the 19th century, the late 1800s, realizing that other things might be blocks into the early part of the 20th century. And so we recognized that all these different atoms are made of stuff that was in some sense common. They got to our next model that we come up with, remember? 3 parts, not in this order. The discovery order would have been electron, proton, and 1930 for the neutron. But when I typed it, I wrote it in this order, and I didn't bother to rearrange it. Okay, so I apologize for that. But we have those basic 3 building blocks. That's probably the atom that we all learned when we went through school, right? The simple idea of a little nucleus of protons and neutrons and electrons orbiting around it, right? And it was really neat. It works well, and it's still a pretty good model. When I was in graduate school, I wound up dealing with electrons and little clouds of them, and they were very much, I envision them that way. Nothing quantum mechanical or anything else like that about it at all as we deal with it. And it's a nice model, but one of the interesting things that happens is we get into the 1940s and 50s, and we begin to realize there's some other things out there, and so these aren't that's a real nice. You can argue this is one better than the ancients, right? The ancients had 4, we're down to 3. That's nice, simple, everything put together. Okay. So we had to go up and play with our model a little more. And so we came up with this thing that we call the standard model. At least we're honest enough to call it model. Right? And it had in it 3 basic families of stuff, right? It had quarks and leptons and bosons. Next, please. So, quarks, depending on where you went through school and what you had, the first couple of quarks we talked about were up and down. Okay, and as we talked about protons and neutrons, one's made of 2 of one and 1 of the other. The other's made of 1 of the one and 2 of the other. It's 2 ups and a down, or it's 2 downs and an up, depending on which way you're going with it. Those are the first couple of quarks that we found experimentally. Next. Okay. Not long after those 2, we found one that would behave very differently. Okay. It was kind of odd or strange, right? And as a sense of thing, this is kind of first generation, the second generation in the mid-70s while I was in college. Because actually, you can argue when I was first started college, it was kind of nice. There were 3 that we knew about, and that was kind of made me feel stupid about proton, neutron, electron. Even though the standard model said there were more. We found charm, okay? And then in the late 70s, we found bottom or beauty, depending on where you went through the education of it. And then in the mid-1990s, Fermilab, thank goodness, just before they ran out of energy, beam energy, okay? Not personal energy. They finally reached top, right? There's a nice Nova show about the quest for top and finding the top quark, which I still think was better when it was known as these were truth and beauty. I like them better than top and bottom, but I don't have any control over that, so we go with the names. Next, sweetheart. Okay. So, what do we know about quarks? Well, we know that quarks never exist alone. You never find quarks by themselves. Or as I guess he's going to say, quarks are never free. They're always bound in some sense. And we call the things that they exist in, we call them hadrons. If it happens to be there's a word I know, man. Turns out every quark has an antiquark. So those 6 quarks have 6 antiquarks. Right? So if you're counting total number of particles that we're getting up, there's already 12 of them there, right? We haven't gone back to the leptons and bosons yet to get to that stuff. But if you put just one quark and an antiquark together, we call it a meson. Next, and we put 3 quarks together, we call it baryons. Protons and neutrons are baryons. Like we talked about 2 ups and a down, or 2 downs and an up. There's a sort of different quark antiquarks. We'll talk about them through more of the talk as we go a little bit later. Next, and in the lepton family, these are particles that they're not made of quarks. They're absolutely indivisible fundamental particles, the most familiar one of which is the electron. Okay? And an electron is an object has a mass of about a little bit over 1/2000th the mass of a proton. It has all of its charge is negative in terms of the sign. It has a unit of charge in it all by itself. It has some cousins. Next. This is the one we talk about more today. This is the muon. It's a heavyweight version of an electron, 200 times as much mass as the electron. Due to its weight, it actually doesn't live real long. We'll come back to details about that a little bit later. Next. And there's the super heavyweight division. There's the tau. All 3 of those things have in common that they're absolutely indivisible, and they have -1 for their electrical charge. To conserve momentum in collisions, it turns out that's not enough in terms of the leptons. There are these things we call neutrinos, little neutral ones, and they come in 3 types. There's an electron one, which is always associated with an electron. There's a muon neutrino associated with a muon, and a tau neutrino associated with a tau. It also turns out that these 3 sometimes oscillate from one type to another, which is peculiar. I can't use strange. I can't use odd. We'll call it peculiar. So those are the 6 leptons. See, I got a fundamental problem here, right? 6 quarks, 6 antiquarks, 6 leptons. This is just our basic building blocks that we're doing it. Okay, sweetheart. Okay. Then there's bosons. Okay. Bosons are the things that are involved whenever there's a collision, an interaction between objects. And depending on the type of them, different types of bosons are exchanged. The first we'll talk about is electromagnetic, because that's the one you may have heard of more often in terms of the bosons, the photon, that's exchanged whenever there's an interaction between 2 objects. It winds up being in the electromagnetic, what we thought of maybe as Q1 compared to Q2, separated distance R squared, like Coulomb's law, that sort of stuff. It's a photon that gets exchanged. When you get down inside the nucleus, there's the strong nuclear force which holds the nucleus together, and this carries the creative name of gluon. Right? There's got to be a little humor in there every once in a while, right? So we've got a gluon. Next, okay. The weak nuclear force has 3 different ones. Okay, we have the W, 2 types of W, and the Z bosons that could all be involved in weak nuclear. Weak nuclear explains radioactive decay. Okay, when parts fly apart. Finally, we get to the gravity force, which is the weakest of all these, and there's graviton. Okay. Time out for a quick commercial plug. We haven't never seen gravitons, but at least we've seen gravity waves. And the DePauw student who was active in our balloon program several years ago was working on his PhD at LSU on the LIGO and was actually there involved with the first detection and has his name as one of the 1,003 authors of the discovery paper. But as a graduate student who doesn't even quite have his PhD, that's a pretty good paper to have your name on. So yeah. So, next thing we have to talk about is energy in particle physics and how we measure it. And typically we're going to measure things in units of electron volts, which has the terribly complicated definition that 1 electron volt is the amount of energy an electron gains if you move the electron through a potential difference of 1 volt. So 1 electron times 1 volt is 1 electron volt. Yes, me? And for those who want to think back in good old metric units in terms of joules of energy, it's the charge of the electron, okay, but converted over because they work into units of energy. Joules, 1.6 times 10 to the minus 19 joules. I'm a 2-digit guy. If you want to do 1.602, you can, but this works. I'm still a slide rule guy. So that's kind of a fun thing to do with it. Next. So let's talk about energy of typical things. Actually, in this room today, we may be bordering on 0.04 eV. If they crank it up much colder, we may get down to 0.03 eV. But room temperature molecules are about a 40th of an electron volt, 500 to make a decimal. Visible light ranges between 2 and 3 EVs. You go to the dentist, right, and take the x-rays and they say, there's nothing harmful here, but they put that lead shield where you run around the corner and they hit the zap button. Don't worry about it. Those x-ray photons are about a kilo electron volt per 1,000 EVs. The Large Hadron Collider over at CERN, which is the most energetic particle accelerator we have at the moment. At the moment, they've reached in a single beam 7 times 10 to the 12th, or 7 TeV. Now, since you can send beam against beam, it gets you up to double that, or 14. Their goal is to actually get to 14 TeV in each circle and slam them together to get to 28 TeV, which is a lot of energy for these little things to have. Next. So, before we go any further, we have to talk about the most familiar equation in physics. This doesn't mean it's the one that we think is the best or the most important of all. But what is the most familiar equation in physics? Time for some suggestions. E equals mc squared. Now, we're a little large college, and I always tell my students that if they would just go over to the dining hall and ask at lunch, what's the most famous equation? They'll tell you E equals mc squared. And just like my students, they don't always remember what, next slide. There it is, in case you had to see it. They don't know what E means, they don't know what M means, and they don't know what C means. They know E equals mc squared, right? And that's true. E is the energy, M is the mass of the object, and C is the speed of light squared. And one of the important things that happens is it turns out that you kind of go back and forth between mass of stuff and energy that objects have. Okay. And so now we're going to talk about primary cosmic rays. Okay, and that's an important thing because it's the primary cosmic rays that allow us to talk about all the energetic particles we can observe and detect when we fly up balloons up into the atmosphere, whether it be the troposphere or the stratosphere, the lower stratosphere. Basically, they're stable, and generally speaking, most of them are charged particles. Okay, stable means they live a long time, or at least a fairly long time, or at least from the particle standpoint, a long time. Because one we're going to have here is not going to be charged, and it's not totally stable, but it's pretty good for what happens here. Okay. Mostly they're protons. Okay, protons are very stable. We think protons decay with a half-life of somewhere around 10 to the 31st or 32nd years. Okay, that's a long time. Okay. There are some neutrons, like I say, those violate the idea of being charged. They also violate the idea of being stable because neutrons by themselves are kind of like the quarks. They don't really heavy. And so after about a half an hour or so, half of them will die. Another half hour, another half of them will die, and that's what's but 4% of that. And finally, the other 1% is everything else that happens to come in. It might be a nucleus of an iron. It might be the nucleus of anything else that could have conceivably come from an explosion of an object. Now, these energies begin to get a little exciting, right? 1 billion electron volts is the low end of the primary cosmic rays. Okay? The high end, okay, is 10 to the 8th, right? That's 100 million TeVs. Okay? Keep in mind, our Large Hadron Collider can do, when they hit each other, 28 TeVs. This is 100 million TeVs. Okay? Extremely energetic things that, in many cases, just fly by through you, and you didn't know it. You ever don't know what hit you? Well, maybe it was a primary cosmic ray. Thanks, Jeff. So, where do these primary rays come from? And the answer is everywhere that something happens. Black holes. That gravitational wave that came was from two black holes that were orbiting each other and decided to run into each other. They really put out a lot of stuff, right? But black holes, that's one death product of a star. Neutron stars, another death product of stars that aren't quite as big as the ones that make black holes. And actually, pulsars are usually rotating neutron stars. So these are all kind of related to the death of stars in terms of the object that's left over after the death. The supernova events, the supernovae are the ones when the stars blow up. Okay? We get primary cosmic rays from the core of galaxies that are being created. In the cores of galaxies where a lot of energy is being converted to mass by E equals mc squared and vice versa, we call them active galactic nuclei. Okay? Quasars are quasi-stellar radio sources. There are still cosmic rays moving around the universe that came from the Big Bang. Okay? And they're doing it. Now, our sun also does something. About 1% of all the cosmic rays that come in are from the sun. Okay, they're probably sent out to us via solar flares that accelerate the particles that are in the solar wind, which are basically protons. However, once again, their energy is low on this sort of bizarre scale we're dealing with. My graduate work was using electrons that were basically thermals. They were between 1 to, on a good day with the right one, 3 EVs of energy density electrons I was working. That's why I thought of a little swarm of them. But they're nice and slow and they drifted through the region. So for me to claim that 600 GeVs is low energy is a bit difficult to say as an atomic physicist, but it is low energy. And so, how do they get the energy? There's several ways. The shock wave, the shock wave that comes from the explosions, most of those devices we talk about were really explosive. Sometimes it comes from the decay of particles, because if a particle has mass and it dies, it gives off the energy from that E equals mc squared, so it kind of goes both ways. And so the particles decay. Maybe some of the energy comes from dark matter and dark energy. I am willing to admit that I think those things might exist, but the details on them are a little bit small and slight, so we'll talk about that. But lots of different ways to get the particles up. That's a lot of energy. I mean, think of what we do. We got this hole in the ground that goes around on a huge radius. There's actually a chunk of a hole in the ground still over in the Dagadocious, right? Because back in the late 80s, we were going to build, in the early 90s, we were going to build a superconducting supercollider, and then we stopped, and boy, that's hard. We were trying to get kids into graduate school, and the government cuts the funding, and people worry about every other funding source to get people into it and all. But even those would have been, superconducting supercollider would have made it up maybe 100 TeV, but we don't have that. So this is amazing. And so particles that have charge are influenced by magnetic fields. And the way they're influenced is that the magnetic fields change the direction of the path, but they don't change the actual speed. They don't change the energy. They just deflect them. Yes. It turns out that the magnetic field associated with the Milky Way galaxy tends to keep trapped. In other words, they can't get out. They wind up going around in a rather long-term orbit. Particles that are below 10 to the 15th EVs, I didn't stay consistent. I should have said it, but I stated TeVs, right? Then we're talking about 1,000 TeVs as we worked through there, but I kind of went back and forth. And the sun's magnetic field does a pretty good job of deflecting the low energy particles. If you have too much energy, you don't even notice the sun's magnetic field. You just kind of fly right on through. You definitely don't notice the Earth's magnetic field. That's why we get primary cosmic rays coming in at all latitudes. Now, there's more near the magnetic poles than there is at the equator, but the variation is only about 10% over that, so it's not much of a change. So we got to talk about inner actions inside our atmosphere, and that's why I had to go to my prop. It didn't roll away, I hope. So we'll talk about that. So interstellar space has a whopping 1 atom in every cubic centimeter. You say, oh, a cubic centimeter, that's not, that's a unit. Too many zippers. There it is. Okay. So, 1 atom in every cubic centimeter. You say, oh, that sounds okay. It's a cubic centimeter. Right? 3/8 of an inch by 3/8 of an inch by 3/8. Oh, I got engineers out here, right? So I better speak in inches right now. So 3 inches.
Thank you.
You're welcome. I do want to get a response from you if no one else. I do a lot of engineering. I'm the take care of the engineering students in the physics program at DePauw, so I admire it. But we have to watch out for those stupid units because we might want to fly to Mars someday. Oh, we did that already once. So, for comparison, what's it mean to say an atom in every cubic centimeter? Atoms, how big's an atom?
Pretty small.
Pretty small. Well, that's a good answer. About 10 to the minus 10th meters. Okay, so just to help you out, I've brought a large-scale model of an atom. If it looks like a giant wiffle ball, it's because it was in our boys' collection of toys out in the garage. And I found it before I found the softball I was digging for, so I said, this will do. So it's softball size, right? That sort of thing. We have this ball, okay? If that's my atom, my cubic centimeter would be the entire volume of the Earth. Did you catch that? The Earth. No, we're not. So that's how empty space is. Imagine if this is all there was in the whole Earth. Well, we'd have problems. We wouldn't be here, we couldn't breathe, all those sort of things. So we'd have those issues. But that's empty. Now, when you get to our atmosphere, we go to the absolute absurdity the other way, right? The density is about 30 billion, or 30 billions of billions of atoms per cubic centimeter. How can I make that comprehensible to anybody? I don't know. We like to count. So let's say we're going to count the atoms in a cubic centimeter. And we'll count it at the rate of 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, right? How long is it going to take us to count the atoms in a cubic centimeter?
Forever.
Forever. That's a good answer.
Billion seconds.
It's going to be 100 billion years. There's pi times 10 to the 7 seconds in a year. Not quite pi, but pi works. I'm a 2-digit guy, right? It's 3.16 times 10 to the 7 seconds in a year, a regular year. We got an extra day this year just to help us out. That's one extra day so we can elect a president and have the Summer Olympics. It all happens with one extra day. So think about the difference between this and that, right? If you started counting now, well, you'd have to count 10 times longer than we know the age of the universe to be. To count all of them in a single cubic centimeter. So, as a result, this is a heck of a statement, primary cosmic rays in the atmosphere probably will hit something. And when that happens, other particles are created. Why? E equals mc squared. You can think of it this way. We go off on the parking lot. Let's find the 2 smallest vehicles on the parking lot. Bill came in a fairly small vehicle. Okay, so he might be one of our candidates. Okay? We're going to drive them down. Don't tell Michael and Louise this. We're going down to an intersection. We got these roundabouts, so they're just fraught for collision opportunities. We're going to have Bill meet a car of a similar size, similar mass. And they're going to collide. I don't care whether it's head on or not. It doesn't really matter. But they're going to hit each other. And we go down to do the post-crash analysis. We see 2 tractor-trailer trucks. Okay? That's what can happen in these collisions. These little things that come in. We talk about protons basically coming in, right? We're talking about getting things out that have a lot more mass than the proton. Because all that energy they had gets converted to mass. And that leads us to some things. So, time for a diagram. Thank goodness. Okay, so we have a primary cosmic ray coming in. What's it going to hit in the atmosphere? Nitrogen. Okay, but that's a different story. It won't be generic. You just say it's going to hit an air molecule. Okay? When it hits an air molecule, it's going to knock it apart. And lots of things are going to come out. Okay? And among them, okay, are some things that we call pions. We symbolize them with the letter pi. There's 3 types of pions. There's the positively charged pion. there's the negatively charged pion, and there's the uncharged, the pi zero. Okay? Those are all one pion. There's also things called kaons. Okay? And the kaons come out as either positive or negatively charged. There are no neutral kaons. Okay? There's neutral pions, but no neutral kaons. So that's what comes out of the first question. Okay? What are kaons and pions? First important point is they are the lightest of the mesons. Actually, the pions are the lightest, the kaons are the next lightest, and there's others that are heavier than that. And to be brutally honest about it, probably in the collisions, some of the heavier mesons were produced, but we'll see in a second, they effectively become kaons and pions. They have very short lives, but they're longer than any of the other lives. What do I mean by short? Neutral pions live for 10 to the minus 16 seconds. That's a nanoseconds to the minus 5, to the minus 9. So picosecond, femtosecond, right? So a tenth of a femtosecond. Okay, 100 attoseconds. Okay. That's not real long. That's short. Yeah. Think about the speed of light is 2.8 meters per second, right? And so light moves essentially in vacuum the length of a piece of standard note paper in a nanosecond, right? And these things are talking about being 10 to the minus 7th, okay, or 10 million of a nanosecond. So for all practical purposes, pi zeros aren't ever here. They just become 2 gamma rays. Oh, kaons live for quite a while. They make it for 12 nanoseconds, right? That's pretty good. And finally, the charged pions, the pi plus and minus, live for a whopping 26 nanoseconds. And that is interesting because actually the lightest ones live the longest. Okay? Just like the electron lives arguably forever, okay? And the muon lives for 2.2 microseconds. Let's see what they're next to it. And so the primary decay process that happens from the meson decays that we get to is actually called the muon. Okay? And the muon is just what happens when the pions and the kaons decay, they become muons. They may actually be mu plus or mu minus because all the particles also have antiparticle relatives that have the opposite charge. What do the gamma rays do? The gamma rays generally die in what's called pair production, and they make electrons and positrons. And as those go around and they fly by other air molecules, there's the braking radiation, the Bremsstrahlung, slowing down as they go around, gives off more gammas and more electrons and positrons, which then see more air molecules and make even more of those things. Okay? So we have a lot of that going on. Okay? What do the muons go to? That's a good question. What's there? Some muons decay into electrons or positrons. We've already got electrons and positrons. Now we got more electrons and positrons. Yes. And but most of them remain muons until they die. And like I say, they have now a fairly long life compared to the things we talked about so far, right? 2.2 microseconds. Okay? So they're fairly long lived. So a lot of the muons actually make it. So what makes it down to us? I'll consider North Texas still the ground. Okay. That actually means that our EOSS folks live above ground because they're up so high, right? But sea level, this numbers come from sea level. So for every 10,000 muons that make it down to the ground, we'll still have about 200 primary cosmic rays that make it to the ground, about 20 high energy electrons that are above a giga-electron volt. Somehow, even though they only live for 26 nanoseconds, a few of those pions make it to the ground, right? And 100,000 electrons come down with us as we go through that. Lower energy on their scale, not my scale. Still energetic from the atomic physics. So, how can we detect the energetic particles? There's two principal methods we can use. One of the easiest, and what several of us have flown through the years, are simple Geiger counters. Okay, Geiger counters, a little tube, gas in it, something energetic goes through, ionizes the gas, you get a spark, pulse, voltage pulse, you count the pulse, click, 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 Geiger counters. Slightly more sophisticated ways that happen are to use pieces of plastic in some cases, scintillators or big collections of them. That's what the accelerators have, to collect them and big things. I know that at Iowa State, they've been working on some panels that are small, that are very balloon ready, that have 2 photometers on the corners to get the light flashes that come as the particles go through. Have a stack of them. You time it. Went through this one, went through that one with them. Know the energy that you have of the particle that's coming through. Maybe even what the particle is if it happens to die in one of them. Have an idea about that. So that's a different way to do it. Jeff Daly and Hank Voss have both left Taylor. Hank retired, and Jeff went out to work with a spin-off company they have, Ventures. They've put together a similar package using scintillation panels. It helps out because Geiger counters do get a lot of counts. They're just no easy counts. So, what can we do with it in ballooning? One of the things that we did, the first experiment we did, is I got into this stuff because when I went back to DePauw and said, oh, I've got a class that starts in 4 weeks called Experimental Methods. I think I'll use high altitude balloons. What's the science we can do? I went down to Hall. At the bar of the Hall is Mary Kurtzman, a colleague for about the last, almost 30 years now. Mary's a gamma ray astronomer. So she studies the showers of particles that come down when the gamma rays enter the atmosphere, to point them back to out towards the object. She works with a telescope array outside of Tucson called Veritas. And so she said, you ought to look at something related to energetic particles in the sky to help them do their models a little better. My next door neighbor, sweet mate, is Alex Kuhlmeyer. He's a nuclear physicist, so we kind of into particle stuff, so that's how we kind of got into this idea. So the very first flight we did, which was in the fall of '06, we decided to look at Einstein's theory of relativity, special rel, at this point, not general rel. And this has been done historically before on the ground, looking for muons with a pair of Geiger counters. Muons have so much energy, they'll fly through one, and they'll fly through another, and ionize them both at the same time, because they're traveling pretty quick. And so the historic experiment was done on Mount Washington, where here's their data. So we have to click this in about 5 in a row. So at Mount Washington, looking at the muons up at the top of Mount Washington, which, here we go, 6,250 feet, okay, compared to sea level. And here's their counts. The top of Mount Washington, they got 563 muons in, I think, a minute. They had pretty good collectors they work with. Classical physics would say, based on that half-life of 2.2 microseconds, and knowing the altitude difference there, so we call it 2,000 meters just to make life easier on ourselves, okay, because that's the easier one to think about it, traveling at 2.2 microseconds. Classical physics would say, okay, here, well, we would expect 31 when they took their rig down to the bottom, down to the sea level, which isn't too far from Mount Washington if you know how to get around in the northeast. The count at sea level was 408. Even in my definition, that's a lot bigger than that. Okay, as we went through that. So you use special relativity of Einstein, and his prediction would say 390. Earlier in the talk, I said I believe in how many digits? 2. So they're the same. They're both 400.
Can you grade that way for your students?
On some places, yes. Some places, they even grade if they get their graph to have the theoretical line and the data on the same graph. Wrong slope, wrong order of magnitude, but that's not, it all depends. And there's a reference for somebody who really wants to know that I didn't lie about it. That goes back to 1963. So, going to high altitude balloon, we've got a chance to change much higher than Mount Washington. So we did it. So this is what they did in the fall of 2007. At 15 kilometers up, they counted with their array, which was some Pasco Geiger counters at that point in time that we haven't used an array. They measured 6,500 muons. Okay. Classical physics would say, okay, think about that, 2.2 microseconds, even if I travel at the speed of light. Okay. I'm talking about going 600 meters. Right? So if I come down every 600 meters, I'm going to lose half the number of particles. So classical physics would say there should be no muons at the Earth's surface. Einstein's relativity predicts 144. That's what the students got as their calculation. And our counters came up with 225. Now I know a 2-digit guy didn't make it anymore, right? Okay, but at least it's still close. And for the first run with it, it was a nice way to go to say, hey, we proved it as well. So another experiment that proved special relativity. So that's where we started with it. And as we moved on, we've done some other ballooning things. I've talked to GPSLs in the past about this idea, about the famous Pulsar maximum. It's perhaps slightly better known than the Hank's knee, but not too far away from. And by the way, I love the data that Mark showed, because you see that nice knee at 58,000 feet that we saw in the descent rate for the balloon that you did. It went to 73. Just a beautiful example of it. That's where the number of particles you count is a maximum, right? It's actually arguably the place where you have the most production happening, because you got the most energetic particles, because they come through a little bit of air, but not gotten too much air, and so we get a lot of particles there. So that's something that we started to try to investigate with some simple Geiger arrays. And here's just a vintage photo, which actually I'm using this so much I actually had narration on this one, so I could stop talking for a moment and let it play, but I muted it, so it's not there. But here you can see our count weights went up, and when it goes, Base 19 was one of those flights that we launched, and we recovered to give the OSS hope still. We recovered 6 weeks later, okay, because it landed in southeast Ohio, hanging in a tree with our nice shiny thermal blanket boxes, just winking in the winter breeze. But a really nice set of counts to show you. It peaked up there somewhere in the mid 60,000s. And so we developed, the way we did that was with a cosmic ray telescope, we like to call it. And we look at the coincidence count at different altitudes for different orientation. And so originally what we flew was we flew pairs of originally we flew Pascals, right? I mentioned that earlier. We have always recovered something from every flight. Occasionally, we've lost parts, and I think this video, it may still be up on the web somewhere. We had a flight for a middle school out of Terre Haute, and I decided to strap a camera, a good old DXG old one, on the side of the top pod, which skewed the center of mass slightly, and that's when I was still using the carbon fiber rods, tubes that Jeff Daly liked to run the cords through from box to box. So we skewed it slightly. We're coming down very nicely in descent. Really, it was not a lot of chaos until this happened. And at about 71,000 feet, the carbon fiber.
It's doing it on.
It's doing. We're in the. I took away the sound, but I didn't away. Okay. That's a picture of the apparatus. That's okay. Don't use your box. We'll catch up. Anyhow, we cut the pods, and so I put the Pascal Geiger counters into. That's okay. Here's the data from the horizontals. It's keeping me on schedule, right? There's the horizontals were lower than the verticals to get the reduction zone, and then the horizontals wind up arguably being maybe above, a little noisy still there, but at least certainly in the range of the verticals. But we cut them off and we dropped the Pascal Geiger counters in the Lake Monroe Reservoir, I think. Unless that's true. Now we got the shielding with lead. And Bruno Rossi did this stuff because we thought we might try to do some energetic ideas. And let's see, sweetheart. We're now safe for you to hit the button. There we go, a little bit of gravity. The idea behind it was that Rossi was working with, and we kind of investigated as well, was we had a Geiger tube inside our aware electronics one, put lead around it, and our count rate went up rather than down. Okay? Because what was happening there is those energetic particles are hitting the lead and creating a shower of other energetic particles. So effectively, we made a larger collector than what we had before. So here's a horrible slide of the data because if you're red-green colorblind, I'm really cruel, okay? And if you're all eyes challenged in terms of dot size, we've got issues here, right? But we ran 3 counters on a flight, base 42, so we're up a couple years later. Tomorrow for us will be base 89. Okay, Grand Island in 07, we flew base 8 there. Okay, so we were hang on a run.
I didn't touch it.
But anyhow, hit the back arrow button. Okay, the blue's no shield, the red's a little bit of lead, the green's a little bit more lead. Okay. Now, if you put enough lead around there, you can actually get the count rate to go back down. That's what Bruno Rossi proved. I've never flown a non-exempt flight. Because the Geiger counters are small and we can still stay under the limit. Okay? Now I got real close to having to have the detector in one box and the lead in another box with the shortest payload string one I've ever seen between the 2 boxes. But we got to the point that 12-pound total string limit was getting to me. Although I thought about packing the GPS tracking inside the experiment because, right, your recovery weight doesn't count in the 12 pounds. So I just want to make sure my GPS is well shielded. No, don't want to do that. So yeah, this worked out pretty well through there to show us that sort of effect. Okay. So now, hopefully, when we go to what's next, we'll stay here for a minute because this is kind of what we're up to. We have changed. We've now gone to 3 Geiger counters rather than 4. That way, you lose one less. And we lost other Geiger counters from operational standpoint, not lost them. We floated. So we remember base 20, which was I talked about at Keith's GPSL at Jewel, William Jewell College, Liberty, Missouri, a fine school. Beryl and I both graduates of that place. When you float Geiger counters across about 25 miles of Lake Erie, they won't work anymore. Okay, so we lost them, or we didn't lose them. You wrap them around a power line, as we did at Upland. You can take the life out of a Geiger counter. So flying 3 rather than 4 is what we're after. So what are we headed to next? Well, at Grand Island, we just flew the 900 megahertz. I had no ham. I had no ham radio. We went out on chase, okay, and everybody else went out on chase. Our radio failed to keep good GPS data on the way back down, but Mark Connor had told us where it was at 30,000 feet, where it's going to be at the ground. We went there, we DF'd the box without Steve's wonderful fancy equipment we used a year later in Kansas City when we had light string separation, you know. But I moved into Hamland, okay, KC9QB, I moved up to General. Okay. The next time I get a group of students, do I have to get them through tech? I guess I'll have to earn my extra because I say, okay, if you're going to take an exam, I'll take an exam. So we'll have to get to that class of it. But here's what we've got in mind next, just in a quick overview, and we'll have some time for questions. We got our 3 Geiger counters. All of the earlier stuff we used the basic stamp. I'm flying one again tomorrow still. See? It works real fine. I keep data up to about 275 minutes recorded on the basic stamp. And yes, most programs on the Arduino go into infinite loops forever. The basic stamp's the same way until you start saving your data in the memory, and you save your data in the memory in the right order, so you get back and you save and you save and you save and you save till you get the loop, and then you stop saving. And then you get the reprogram and you read it. So I mean, that's what we did with the old stamps. We graduated to the Arduino this spring. We went to, was it the GPSL? I don't remember how many years ago we came away with an Arduino. They were maybe from the High Altitude Balloon Conference. We came away with an Arduino Mega, which is a nice Arduino to come away with. Right? And so we're controlling the 3 Geiger counters with an Arduino. Okay. Eventually, if I can make sure we don't have a pin conflict, thanks to Zach this morning for that bit of advice, we're going to put Zach's Arduino tracker on top of it and allow us to bring the data down from real time with a APRS. Just put it into the next string. We'll bring the digits down. Tomorrow's flight, we're flying the Arduino and the 3 Geiger counters. Since we were still having issues with getting to talk to the Arduino tracker, we backed up to our Zigbee conversation with the 900 megahertz, and we have 34 lines connected between the Arduino Mega and our 2 sets of Zigbees, which have the 10 analog and the 8 digital lines, so 36 lines. I got 2 left over to give us the Geiger counter counts back in real time on the 915 megahertz. But the real plan is, I've noticed over the last couple of years, we've done 2 different things, right? Ron, K6RPT out in California, did some of his nice, take a perfectly good 3,000 gram balloon, which might cause the USS guys to wince, and hang 3 ounces on it. And give it enough positive lift for 200 feet per minute ascent rate. You'll get up, and as we showed, the rubber will not break. You cannot get enough stretch to stretch the rubber to break, and you can float, as Ron did up there to roughly 120,000 feet and come across eventually the latex skies. One of them was a short trip. It landed just a little bit southwest of Greencastle, and I went out and recovered it. The other went across to Morocco. Right? And did that sort of stuff. And then, of course, we've all gotten excited. Bill's got his wonderful device with him there. These Pico sets, right? where we just take mylar balloons and fill them. So I'm going to be developing a mega picosat. So my mega picosat is going to carry, hopefully in one small package, this sort of stuff, cutting weight every way we can. So we'll probably, we wish to take the little Geiger tubes ourselves, make our own supply for it, single supply, cut weight every way we can, and then use a simple super pressure. I'm leaning towards the plastics, because as the whole world knows, Putnam Plastics is in Cloverdale, Indiana, and that's what they do all day long, is make roll plastic sheeting. And if I go down and talk to them, I might get them to make a piece even the length I want, the thickness I want, and make a bag, pretty big bag, but I'm going to hold up. I've got some, I can't get around the weight issues. I'm not, what'd you say, it is 14 grams? Is that what yours is, Bill?
Yeah.
Okay. I'm not going to be at 14 grams, okay? I'm going to have more than 14 grams of lifting gas, right? I'm going to have a bag that's going to be worth it. But that's the plan, is to go up, and the real reason to stay on APRS is I'm up there, I beep, somebody down here is going to get it recorded, and I can actually sleep while I'm sitting down there. My students won't. I should at least say my students shouldn't. I've gone out on I call it tracking and recovery, because when people stop you that have the decorative lights on their car, it's real nice to not say I'm in a chase vehicle. I'm in a tracking and recovery vehicle. That's what my little magnetic signs that kept blowing off the car say. They're supposed to stay awake to let you know where it is. And sometimes the car gets real quiet and kind of, Shelby, John, where's the balloon? Oh, okay, I got myself. But they can help us get this stuff down. And there's no secret, like if you want to know, we're throwing away the lowest few bits on the Geiger counters, because who cares? It's only the high bits that matter on that. The coincidence is we use the right number of bits to bring it down. We'll have a little string with 5 values in it, GC1, GC2, GC3, as I called them. My students this spring came up with a whole new way to call it. Okay? So they're labeling these things T, M, and S for top, middle, and side. The only problem was I still labeled my Geiger counters in big red Sharpie, GC1, GC2, GC3, and 4, 5, 6, 7, 8, and the numbers they picked are not in the same order as what I had. So I had fun putting it back together today, because they had a couple of loose wires. I moved the box. But that's our long-term plan. I'd like to go up this time of the year. I'd like to go up in the dead of winter, which will be a little more exciting because of how I get it. 60 to 80,000 feet stays pretty calm most of the time at all those things, but you're still getting to where you might go east or west. But I like to stay up there because the Pulsar maximum, going way back to that, does it vary with season? Does the altitude change? Does the intensity change? What about the overnight versus the daytime? I mean, the sun's doing a little bit of stuff. I don't know if we're going to see 1%, but it might be fun to look for that and see what some perfection see. So that's sort of the plan of where we're next. And I would anticipate that the ways the flights work for us, that having this thing really work and being downlink is probably 2 or 3 years out. So based on my conversation with the 2 Pella guys sitting in the car with me yesterday, at one of their GPSLs, that was that they're going to host the next 3 years in a row. I understand it. One of those we'll be able to talk about it. Okay, maybe 3 years out before we get to it. But it's fun to look for them. And the small Geiger counters work well. I know Paul's flown them a lot, and several of the others of you guys have put them up. They work well. And it's a neat thing for the kids to see that. And the other thing that happens is I took the data from our last flight with the middle school teachers and high school and elementary school teachers in town last week, and they were looking at just the count rate from the Geiger counters, and rather than showing it as I did there where I had count versus altitude, right, I flipped it the other way, right? We flipped it the other way. They said, oh look, where does the highest counts, okay? And they're saying, oh, it got up there pretty high, and even at 30,000 feet, at 10 kilometers, right? And up in the, so where are those airplanes flying? I don't know. What's happening? So it's kind of one of those things just fun to think about. It was not as interactive as I intended it to be, but I appreciate your attention. Other questions?
How much do those Geiger counters cost?
Yes, I haven't bought any for a long time. How old are you gonna come?
They were 150, they jumped up to 170.
170, yeah. And SparkFun has a version of almost the same thing, sitting on a board without the annoying plastic case around it. And it's about that same range. I think it's about that same. So they're a little bit under 200 a piece. So that's, yes, yes,
What's
sir.
the model number of the tube in there, the Geiger tube?
Do you remember, Paul?
It was halogen quenched.
Yeah.
I
I can't remember.
Sparkfun? I'll go look it up.
Yeah, SparkFun has basically the same tube on it. Okay, I'm sorry, that's one of those numbers that I got. Bill?
Do you have any problems with arcing that in their vacuum conditions?
No. I've seen no problems with the RM60 version. Like I say, the scary thing for me, right, is I think to save weight, I'm going to wind up putting 3 of them off of the same board, and I worry about those sharp points on my soldering skills. So we'll hopefully get someone who's smoother at soldering and doesn't pull his own hats off. Yes, sir.
Does the orientation of the tube affect the count rate?
Not really, because we've flown, just as we talked about, as Mark talked about earlier, we use that 3-axis thing to watch how the box tips. It doesn't appear to pick up. I mean, yes, there are more still coming down here. There's more verticals down here than are, but it doesn't matter too much. I like to maximize them for thinking about stuff coming down, so I lay them. The tubes are actually coming, this is sort of a tube pointing towards us in the RM, is what I was doing with this. So I lay them horizontally. You get a slightly different rate if you ran them upright, because of the coastal cross section, but not bad. Yes, sir.
The scintillation detectors?
I have not. Okay, I've had friends who've flown them. Okay, and it's one of those things that actually the way I'll typically get one now is I'll do something else for somebody, and they'll say, "Oh, here, go play." I'm probably going to get into the satellite version of this stuff by getting photo boards away from the people that are flying those. But like Bill generously last year sent me an Iridium tractor that I flew for the Boy Scouts, and he said he'd come to see the Boy Scouts and get around to it. So we'll probably fly that one again into this stuff. Yes, sir.
How about noise in the radio when that tube walks?
Well, that'll be the fun thing to watch, okay? Because this is the first time I'm talking about flying the tractor that close to the tubes. Okay, that'll be an interesting thing just to pay attention. Because at the moment it's no problem because I've always got the trackers and my satellite separated. And if I have to separate by distance, that's still not the end of the world. And as long as I go with minimalist, Bill Brown, small cell, bubble wrap. I get it.
I've flown probably within 6 inches, and I've never seen a
Okay, you need 6 inches. Okay, that's good. Or 15 centimeters for those who need to think. And so what happened tomorrow? Our bottom box is one of these classic things. You'll say, "Who flies?" Talking about streamlined earlier this morning. I fly anti-streamlined. This will be a rectangular box. This is actually a box we first flew the first year. And we're still using it every once in a while. I have the Geiger counters in one section, the single Geiger counter in another section, and those little Contour Roam 3 cameras out the end, because this is a flight to fly a camera because we see each other every once in a while as we go up. So I've got to fly a camera for this one also. I'll show you the bottom. But it still is 3.5 pounds, okay, of weight, and my other things are 1.5 pounds. So that much weight at the bottom will still get around most of the cameras. So it is fun to watch the video of what happens with the balloon rim as it swirls and comes down. I had one a couple of months ago, came down and for a while went down and wrapped around the descent cord of this payload string, then it unwrapped. And it landed up just perfectly high in the tree. The bottom box was down about the ceiling from where I am, and I had a younger colleague with me, and he shitted the tree, and we pulled it all down and left the picture. Thank you for your attention, and I'm sure we're getting hungry.
Yeah, absolutely. There were teachers like you when I was taking physics in college. You're a lot more fun. Before we